Hello everyone. I am Dr. Chiranjit Ghosh, Assistant Professor in the Department of ECE. Today, I'm going to discuss about the different types of fiber and make a comparison between them. So, in the last class or in the last videos, I had discussed that there are mainly two types of fiber. One is called step index fiber, another is called graded index fiber. Step index fiber means a fiber which has a uniform core refractive index throughout the core and then undergoes a step change at the cladding boundary. Okay, so normally what happens, we have a fiber. In a fiber, there are mainly three sections. One is the innermost section is called the core, which is having high refractive index. Next, outside the core, there is a cladding that is a lower refractive index. Outside the cladding, there is another coating that is made of a plastic or polymer, that is jacket, that is used for protection. Now, this core, this core refractive index, which is very high, if it is maintained homogeneous all along the core, that is, if the density of the if the refractive index is same along the core at every places within the core, if the density is same, then that is called step index fiber. Okay, what happens is that you can see this is the refractive index profile here to here. You should see this is the core. It is a core refractive index, so it is maintaining same. As it goes to the cladding boundary, what happens? It undergoes a step change because cladding is a lower refractive index. So as soon as it goes to the cladding boundary, it makes a step change in the refractive index. So that's why it is called step index fiber. It makes a step change in refractive index at the cladding boundary, and mathematically it can be represented by this formula. So there is the two types of fiber, step index fiber. One is the multi-mode step index fiber, and another is the monomode, single mode step index fiber. Multi-mode means multiple modes can propagate. As I've already told that if the fiber diameter is very high, then it is possible to propagate multiple modes, or you can say multiple rays. Here you can see 5 rays are propagating. So that means I can say that there are 5 modes. Okay. Here, so this is called multi-mode fiber. Here, what happened? Only one ray is propagating. That is the axial ray. So it is called a single mode fiber. So mainly the difference between the single mode and multi-mode is that only one mode will propagate in a single mode fiber, and in multi-mode, many modes or multiple rays can propagate. That depends on the fiber diameter. Okay. But these two falls under the step index fiber. Another type of fiber is there that is called graded index fiber. As I've told, discussed in the last lecture, that in graded index fiber, the refractive index is not constant. You can see here refractive index profile, it is not constant, but it is gradually varying. It's maximum at the center of the core and gradually decreasing towards the cladding. So the shape may be triangle, maybe parabolic, maybe rectangle, maybe like any other shape, depending on your fabrication. And it is observed that among all the shapes, parabolic index profile provides the best result. Okay, the graded index profile, which at present produces the best result, is alpha equal to 2. That is the parabolic index profile. Okay, that means if you fabricate a fiber with a parabolic index, that is, if the core refractive index is varying parabolic with radial distance r from the center of the fiber, then that type of fiber, or then that type of graded index fiber will be very high, will give high performance. Okay, but then the question comes, so obviously we can see that graded index fiber is very difficult to maintain because we have to maintain perfectly parabolic. Now perfectly parabolic is very difficult to fabricate. So then why you are going to the graded index fiber? So there exist two types of problems for which graded index fiber was introduced. First is related to your dispersion or multi-path dispersion. Second is attenuation or loss. So Briefly, dispersion or intermodal dispersion is that I can say, see, in a multimode step index fiber, what we have found, suppose this is a multimode step index fiber. This is a rough diagram of a multimode step index fiber. This is the fiber input and this is the fiber output. Okay. What I told in multimode step index fiber, different rays will propagate, different modes will propagate. Okay, different rays mean different modes. So here if I say there are three rays propagating. One is the axial ray, another is one oblique ray making some angle, another oblique ray which is making some another angle. Okay, so these three rays are propagating. Now the fact is that suppose this is the length of the fiber. So out of these three rays, only the axial ray will propagate faster, or you can say only the axial ray will propagate shortest distance. The distance between fiber input and the fiber output is very short for axial ray because it is propagating straight down the fiber port axial ray. If you see this ray is actually propagating a much longer path. It is traveling much longer length or path. Here it has to go from here to here, then again here to here, then here. So obviously the length that it is traveling, this ray is more. So obviously what happens when it will reach the fiber output, it will reach at slightly delay. Okay, this ray, axial ray will propagate at early. It will come to the receiver at early. This ray will reach the fiber output with some delay. Again, another ray, this is also having multiple reflections, but we can clearly see the distance that this ray is traveling is much more than the other two. So this third ray will reach the fiber output at much later time. So what is happening is that these three rays are actually making your pulse. Your input pulse is made up of three rays. So initially these three rays were at the same position, but due to the fiber geometry or fiber structure, these three rays are propagating different path length or different distances. As a result, they are reaching the fiber output at different instance of time. So what happens? This output, when you are measuring, this output will be the sum of all these delays. Okay, the output which will measure actually is the sum of all delays, all these delays. So what will happen if the input is a very sharp peak pulse? Your output will be a broadened pulse. Okay, so that is here. It is written here. So a pulse traveling along a fiber will propagate several different paths and emerge at the other end of the fiber at slightly different times. At the output end or the other end of the fiber, the signal will be the sum of all these delayed signals. Okay, the delay will be smallest for planar wave propagating straight down the fiber core. That means the axial wave will have the smallest delay because it is propagating the shortest distance, while the delay for the highest order mode. Highest order mode means the ray which is propagating at a higher angle. Okay, higher order mode means the angle which it makes. Suppose this is a zeroth order mode, this axial ray, because it is making zero angle with a fiber axis. This may be first order, this may be second order. So depending on the angle which a particular ray makes with a fiber axis, an order is there, and it is a increasing order. Okay, so as the order increases, so what will happen? It will travel more path length, more distances. As a result, it will reach the fiber output at later time. Okay, it will take more time to reach the fiber output. So that is what is given here. Now, what happens? Ultimately, when they reach the fiber output, it will be a broadened pulse. Okay, this is a very one of the main limitation of fiber optic communication, that dispersion. Another problem is there non-linear effect, but this is the one of the main limitations that is called dispersion. So what happens with this intermodal dispersion or multiple dispersion? Because of these rays traveling at different time, your pulse will be broadened and your bit rate will be reduced. Information carrying capacity will be reduced. So we have to eliminate this dispersion. So one way to eliminate this dispersion is by using the graded index fiber. That's why graded index fiber was introduced. Why? See, the root cause of this dispersion was that this is the same thing which I discussed earlier. The root cause of this dispersion was that different rays were propagating different length. Okay, different rays are propagating different path length. So we have to somehow make sure that when these rays are traveling and reaching the fiber output, they reach the output at same time. So what to do? We can't change the length. We can't change the length of a particular ray, okay? Because they are dependent on the angle. So we can't change. What to do? Can change the velocity. Okay. What we will do is that if you made this core diffractive index varying, which is in a graded index fiber, the core diffractive index is not constant. So it is varying. So what happens is that the velocity also is varying. We know the refractive index is inversely proportional to the velocity. So if the refractive index is high, that means velocity is lower. So what happens is that in a graded index fiber, we already have seen the refractive index is highest at the center of the core, while it is lowest as it goes towards the cladding. So what happens? The axial ray, axial ray, which was propagating a shortest length, now is traveling to a high refractive index, very high, because at the center of the core, the refractive index is high. So what happens is the situation is that the axial ray is propagating a shortest distance, but traveling with a less velocity, very less, because high refractive index means less velocity. So it's propagating shortest distance, but the velocity is very small. On the other hand, this oblique ray, which was propagating a longer distance, but now they are traveling with a much higher velocity because the refractive index is decreasing. If you see, the refractive index is decreasing towards the cladding. So the higher order rays are traveling more faster than this. So what happens is that ultimately these two rays, there is a possibility that these two rays can meet at the output at the same time. X-ray ray is propagating shortest distance, but with very low velocity. Oblique ray is propagating a longer distance, but with higher velocity. So you can know S equal to Vt. So S is less, S is more, but V is less. And another thing, another way is that S is less, but V is more. Okay, so what happens? C becomes constant. So that's what it is saying. So it is a possible that all these rays will merge at the fiber output. So this is why graded index fiber was introduced. But so this is what it is saying written here. So the core diffractive index is maximum at the core center and minimum at the core cladding interface. So that's why what happens? The ray propagating the fiber axis takes the shortest path, but now travels more slowly as the refractive index is larger. On the other hand, the oblique ray is now propagating a lower refractive index where they travel faster. So that's why by suitable choice of this refractive index profile, there is a possibility that all these rays can arrive at a fiber output at the same instant of time. So this was the concept behind this graded index fiber. So this was the main concept, and accordingly it was done. But we all know that the fabrication of this graded index fiber is very difficult. So the perfect profiling, you can say perfect perfect variation of this refractive index has not been possible practically, because we have to make sure that refractive index is varying perfectly parabolic in nature, not triangle or not a rectangle. It should be a perfectly parabolic, but obviously parabolic fabrication is very difficult. So that's why it is written here. Hence, the delay between the rays is never practically zero, though it may be very small. So obviously, graded index fiber has a much more bandwidth, or you can say has much more information carrying capacity than a multi-mode step index fiber. However, after that, single mode fiber was introduced, where the diameter was made very small so that only one ray is propagating. If only one ray is propagating, then there is no concept of intermodal dispersion. Okay, now that is the single mode fiber that was developed. But before single mode fiber was developed, there was a significant interest in the graded index fiber, multi-mode fiber, because of lower dispersion. Another main advantage of graded index fiber is that it has a very low attenuation than the comparable step index fiber, because you can see from here only, from diagram only, if you see this is a step index fiber and this is a graded index fiber, we can see that every ray is touching the cladding boundary. Okay, it's every ray, whether this is a higher order ray or lower order ray, every ray, except the axial ray, every other ray is touching the cladding boundary. And we all know that these are not these are not mirrored. Okay, these are actually forming by refractive index variation, total internal reflection. So obviously these cannot reflect totally 100% of light. Whatever percentage is given, maybe 90% of light will be reflected, 10% will go. Again here, 90% of 90% of light will be reflected, 10% will travel in the cladding. So obviously what happens is that at each reflection, some light is always is getting lost in a cladding. So obviously the intensity is very, very small in a multimode step index fiber, because as the length goes, the ray intensity gets lower. On the other hand, greater index fiber, only the extreme rays, only the highest order ray is touching the cladding boundary. All other rays are concentrated within the core. So that's why they are more highly, what is called, they do not suffer the intensity loss. Okay. Here the intensity loss was there much more, because every ray was touching the cladding boundary. Here only the outer boundary rays are touching. So obviously the intensity is much more in a greater index fiber. So that is why greater index fiber has two main advantages. One is the dispersion. Intermodal dispersion is very less in greater index fiber compared to a multimode step index fiber. Second, the attenuation is also very small, because, as I said, the higher order rays, the fields are more distributed towards the edges of the guide. Sorry, because the intensity in the greater index fiber is more concentrated at the center of the fiber. As I told that mostly all the rays are concentrated within the core of the fiber. So that's why there is very less loss of intensity. On the other hand, in a multimode step index fiber, all the rays are touching the cladding boundary. So there is a great loss of intensity. Okay, so these are the main two advantages for which you are using the greater index multimode fiber, greater index multimode fiber. So this is a brief comparison of this thing. Yeah, this is the cross-sectional view. So this is step index multimode fiber. Diameter is 50 to 200 micrometer core. Okay, cladding diameter is same for all multimode, step, graded, or step index. The cladding diameter is same. Only the difference is the core. For multimode, should be 50 micrometer to 200 micrometer. For single mode, it should be 5 to 10 micrometer. So this is a multimode step index fiber. As you can see, this is the input pulse and this is the output pulse. So you can clearly see the input pulse is very sharp peak, but the output pulse has got more attenuation, and it has broadened also. If you see broadening, it's not perfectly drawn, but if it is a very sharp peak pulse with a very high amplitude and a very low spectral width, here the intensity is very less, and also the spectral width is very more. So it is a due to dispersion and attenuation problem in multimode step index fiber. This is the concept of graded index fiber, which is a parabolic index. So what happened? Here the intensity, it is the input signal. So you can see the output signal. So obviously the output signal has much more intensity than compared to the multimode step index fiber. Also the spectral width will be much less than this. Okay. Here the output will not be exactly similar to the input, because there will be some dispersion, some loss will be there, but at least it will be greater than step index fiber. Next came, after this, it came the single mode step index fiber. Okay. Here, obviously, since only one ray is propagating, this is a step index fiber. But here the mode is only one, because the core diameter is so small that only one ray is propagating. If there is no other ray is propagating except the axial ray, then no concept of multimode dispersion. So obviously the signal will be very high. Of course, there is another type of dispersion happening in single mode fiber, that is a chromatic dispersion and waveguide dispersion. We will discuss it later. But mainly the intermodal dispersion is zero here. So you can see in the concept of intermodal dispersion or multiple dispersion, we have a very high intensity at the output. So this is all our, this is same thing here, it is said here. So we can see the bandwidth is high for multimode, monomode step index fiber in single mode. It's middle between the greater index fiber, and it's lowest for multimode step index fiber. So single mode fibers are, so a question asked, which type of fiber is suitable for long haul communication? So always we have to note the single mode step index fiber is used for long haul communication. Okay, because it has less dispersion, no dispersion actually, very minimal dispersion, and also it has very less attenuation. Okay, so that's why single mode step index fiber are useful for long haul communication. There is a research going on single mode graded index fiber, but there are also some problems is there, and it is not very great performance. Okay, so right now single mode step index fiber is the primary choice for optical fiber communication. Next to single mode step index fiber is the multimode gated index fiber. As I told, the multimode gated index fiber has a lower means is better than multimode step index fiber, but obviously it will be not as much great as a single mode fiber. So it is in between the step index multimode and the step index monomode. And of course, multimode step index fiber is not used. It's only used for only kind of sensor. Okay, in sensors you can use it because where we do not have to deal with any communication thing or any information capacity. So there only our primary requirement is about the what is called light power intensity. So multimode step index means high power intensity we are getting. So for short haul, like say 1 meter or 2 meter length, then you can use multimode step index. Okay. Otherwise, in communication purpose or for long haul communication, like greater than 5 kilometer or 1 kilometer, we need single mode step index fiber. So this is all about today. Thank you.